Hi, today we will discuss design methods and requirements. First, we will tackle the objectives of design. A structural engineer is a member of a team that works together to design a building, bridge, or other structure. In the case of a building, we have different professionals. The architect generally provides the overall layout. The mechanical engineer designs the mechanical systems. The electrical engineer designs electrical systems, and the structural engineer designs the structural frames and components. The structure should satisfy four major criteria, that is, the appropriateness, economy, structural adequacy, and maintainability. For the appropriateness, the arrangement of spaces, spans, ceiling heights, access, and traffic flow must complement the intended use. The structure should fit its environment and be aesthetically pleasing. For the economy, the overall cost of the structure should not exceed the client's budget. Frequently, teamwork in design will lead to overall economies. And you will see later on when you are practicing, this is one of the number one problem in construction because your client will really look for a lower budget. For the structural adequacy, it involves two major aspects. First, a structure must be strong enough to support all anticipated loadings safely. Second, a structure must not deflect, tilt, vibrate, or crack in a manner that impairs its usefulness. And lastly, for the maintainability, a structure should be designed so as to require a minimum amount of simple maintenance procedures. For the structural design process, we have the main objective, that is to ensure that the structure is able to withstand the load effects with an appropriate margin of safety against failure. If you say load effects, these are the bending moment, shear force, axial force, torque, deflection, and vibration. So your structure should be able to withstand all these load effects within an appropriate margin of safety against failure. What is failure? Failure is a condition where the structure ceases to fulfill its intended function. Failure occurs because the structure has achieved its maximum resistance and can no longer carry the imposed loads. Or although it can still carry the loads, take note, because it has undergone excessive deformations that have rendered the structure unusable. So it's not necessary that since the structure can still carry its load, then it has not occurred failure. But if it undergone excessive deformation, we can consider it already a failure. Structures must be designed to be both safe and functional or serviceable. Also, strength and serviceability, that is the limit on deflection, is taught as the limit state. So normally we design according to strength and serviceability. The design process is a sequential and iterative decision process. So take note, the three major phases of the design process are the following: the definition of the client's needs and priorities, development of project concept, and design of individual systems. For the limit states, when a structure or structural element becomes unfit for its intended use, it is said to have reached a limit state. The limit states for reinforced concrete structures can be divided into three basic groups. That is strength limit states, serviceability limit states, and special limit states. So when you design your structure according to these three limit states. This strength limit states involves a structural collapse of part or all of the structure. Strength limit states should have a very low probability of occurrence. Take note, it should have a very low probability of occurrence because it may lead to loss of life and major financial losses. We always protect the loss of life. The major strength limit states are as follows: loss of equilibrium of a part or all of the structure as a rigid body, failure of critical parts of the structure, progressive collapse, formation of a plastic mechanism, instability due to deformations of the structure, and fatigue. For the serviceability limit states, this involves disruption of the functional use of the structure, but not collapse per se, because there is less danger of loss of life. A higher probability of occurrence can generally be tolerated than in the case of the strength limit state. The major serviceability limit states include the following: excessive deflections for normal service, excessive cracks or crack widths, and undesirable vibration. Take note, serviceability issues such as control of deflections, vibrations, and cracking are mostly a function of the stiffness of the member. That is EI, where I for rectangle is I is equal to P its cube over 12. So if you have a higher or a larger stiffness of your member, then you will have a smaller problem with deflections, vibrations, and cracking. Take note that for the excessive deflection for normal service, this is caused due to machinery to malfunction, may be visually unacceptable, and may lead to damage to non-structural elements or to changes in the distribution of forces. Also, for the excessive crack widths, although reinforced concrete must crack, take note, reinforced concrete must crack before the reinforcement can function effectively. It is possible to detail the reinforcement to minimize the crack widths. So take note, we are not looking forward na mawala ang cracks, but we want to minimize the crack widths of the reinforced concrete. For the undesirable vibrations, this is rarely a problem in reinforced concrete buildings. For the special limit states, we have this class of limit states which involves damage or failure due to normal conditions or abnormal loadings and includes damage or collapse in extreme earthquakes, structural effects of fire, explosions or vehicular collisions, structural effects of corrosion or deterioration, and long-term physical or chemical instability, which is normally not a problem with concrete structures. For the limit states design, this is a process that involves the identification of all potential modes of failure. That is identification of the significant limit states. It can be strength limit states, serviceability limit states, or the special limit states. The determination of acceptable levels of safety against occurrence of its limit state, and structural design for the significant limit states. For buildings, the limit states design starts by selecting the concrete strength, the cement content, the cement type, supplementary cementitious materials, water cementitious materials ratio. This is what we call the water cement ratio before, but the code actually give its name water cementitious materials ratio now because we normally mix with other cementitious materials. Also, the air content and cover to the reinforcement to satisfy the durability requirements of ACI Code Chapter 19. Next, the minimum member sizes and minimum covers are chosen to satisfy the fire protection requirements of the local building code. So take note when you are designing reinforced concrete, by choosing the minimum member sizes and minimum covers, we satisfy the fire protection requirements. Design is then carried out starting by proportioning for the ultimate limit states, followed by a check of whether the structure will exceed any of the serviceability limit states. Take note that for a water tank, the design of it is quite different. The limit state of excessive crack width is of equal importance to any of the strength limit states if the structure is to remain watertight. Water tank should be watertight. So in this case, the excessive crack width should be checked first before the strength limit state. So in this kind of structure, the design for the limit state of crack width might be considered before the strength limit states are checked. Also, we have the strength and stiffness. The proper design of a reinforced concrete structure is consists in the judicious selection of member size and material strengths to provide the structure with enough strength and stiffness to ensure that both safety and serviceability are satisfied. Also, we have other aspects of design, that is proportioning of members for cost effectiveness and ease of construction. Of course, you will have a very good design, but in applying it in the construction, it would be really complex, then it would be useless. So you have to design also in terms of ease of construction. Also consider where appropriate the maintenance and statistics. Normally we forget the maintenance because after the construction there will be the operation phase, and during the operation phase you need to include the maintenance aspect. And aside from that, structure should be aesthetically pleasing. Do not design a structure which is not pleasing to the eyes, because it would be good for us if we have the structure with aesthetics. Note that in practice, the engineer must satisfy all aspects of structural design while ensuring an economical design of the structure. Also, we have the structural safety. This is very important. The structural safety is a matter of public concern and the most important objective. And also, we have to satisfy the structural safety requirement. Structural components must be adequately proportioned to have enough strength to resist the effects of the anticipated loads. Force, in this case, you need to consider, or in our design, you need to consider all the limit states, the strength limit states, the serviceability limit states, and the special limit states. And towards that end, we need to consider the structural safety, because we need to protect the life of our occupants. Do not neglect that one. We will continue our discussion for the next video.